Have you ever marveled at how incredibly fast and responsive your smartphone is? Or, how massive data centers handle staggering amounts of information almost instantly?
Yeah, it's pretty amazing stuff.
It's not magic, obviously, it's brilliant engineering. But have you ever stopped to wonder how the different complex parts inside those tiny chips manage to talk to each other so efficiently?
It's a fantastic question because that communication, well, it's absolutely critical. Today, we're doing a deep dive into the Advanced Extensible Interface,
Mm-hmm.
or AXI.
AXI.
Think of it as the central nervous system, maybe, or like a superhighway system right inside modern ships. It's not just some technical spec. It's really the fundamental backbone for system-on-chip or SoC designs.
Exactly. Like imagine a bustling city.
Yeah.
Yeah, you've got different districts, the CPU over here, graphics there, memory somewhere else. AXI is that ingenious network of expressways, those dedicated lanes that let all these diverse IP blocks, the intellectual property blocks, communicate.
And communicate with high performance, point-to-point, all within one
Real.
chip. Our mission today is to unpack AXI's basic purpose, look at its really clever channel-based architecture, and show you how this on-chip communication bus protocol as part of AR's AMBA family makes everything work, from simple data transfers to incredibly complex high-speed operations.
Right. We want to give you a clear, sort of actionable understanding of this foundational tech that powers so much of our digital world, but hopefully without getting too lost in the weeds, in the jargon.
Exactly.
So why AXI? Why is it such a big deal? Before AXI, getting different functional blocks onto one chip.
Well, it sounds like it was kind of a nightmare, right? Like trying to get people speaking different languages to agree on complex contracts without a translator.
That's a great analogy. It was often bespoke, slow, prone to errors. AXI really did change that landscape completely.
So how did it change things?
Well, a huge part of it is just how widespread its adoption became. And a major reason for that is its open, royalty-free specification from ARM.
Ah, royalty-free. That's key. Absolutely.
Yeah.
That accessibility dramatically lowered the barrier to entry. For IP developers, for SoC designers, suddenly everyone had this sort of universal translator for talking on the chip. It fostered this massive ecosystem of compatible IP blocks, development tools.
And when you get that kind of standardization, what's the practical impact? I mean, for the designers.
Oh, the impact is huge. It simplifies the design process significantly, and it drastically accelerates time to market for complex sockets. Designers can essentially plug and play these pre-verified AXI-compatible IP blocks.
Instead of custom designing every single interface.
Exactly. You're not reinventing the wheel every time. This isn't just a small improvement. It fundamentally shifts how designers approach chip architecture. It enables much quicker innovation.
Fascinating. So, okay, at its core, how does this communication actually happen? What are the basics on AXI?
Well, it boils down to two fundamental roles.
Yeah.
You have a master device and a slave device.
Master and slave. Okay.
The master is the one initiating a transaction, like, say, your CPU wanting to read some data.
Okay, the initiator.
Right. And the slave is the device that responds to that request, like a memory block, providing the data.
Makes sense. And you mentioned a channel-based architecture earlier. How does that make it fast?
Ah, yeah, that's a key differentiator. Let's go back to that superhighway analogy. Instead of one single road where addresses, data, control signals, responses all have to sort of jostle for space.
Yeah, traffic jam.
Right. AXI provides separate independent lanes, these channels for different types of information. Addresses travel on one channel, write data on another, read data on another, responses on others.
Okay, so separation is key.
It's fundamental to its high performance. It enables parallel operations. You can do things at the same time, which, vastly boosts the overall system throughput and really cuts down latency.
Can you give an example of that parallelism?
Sure, a write address can be sent down its channel while data from a previous write operation is still flowing down the write data channel. They don't block each other.
Wow, okay. That sounds incredibly efficient. And it's also burst-based, you said. What does that mean in simple terms?
Yeah, burst-based. It adds another layer of efficiency. Instead of the master sending a separate request for every single tiny piece of data it needs.
Like asking for one word at a time from a book.
Exactly. Instead, a single request can trigger the transfer of an entire block or burst of multiple data items, like asking for a whole chapter, or maybe even the whole book, with one request.
Okay, like a bulk delivery.
Precisely. You send one address, and you get back, say, 16 chunks of data. This is super efficient for moving large amounts of data, like loading a picture or a program segment into memory.
Okay, so we have these separate channels, efficient burst transfers. Sounds great. But how does AXI make sure data actually gets from A to B reliably? without losing bits or getting corrupted.
Right. Reliability is crucial. And that's where the AXI handshake comes in. It's actually a remarkably simple but powerful secret to its reliability.
The handshake. Okay.
Every single AXI channel, whether it's carrying addresses or data or responses, relies on this two-signal handshake mechanism. The signals are called X-valid and X-ready. The X just means it applies to the specific channel, like OVLID, W-valid, etc.
So, like a polite synchronized conversation, if I'm the sender, my valid signal basically says, hey, I have valid information ready for you.
Exactly that. And if you're the receiver, your ready signal replies, okay, I'm prepared to accept your information.
And the transfer only happens when?
Only when both the valid and ready signals are asserted, meaning they're held high during the same clock cycle. That simultaneous high state is the handshake.
Like two hands meeting to pass something safely.
Perfect analogy.
That's brilliantly simple. And I guess this two-signal dance is critical for preventing bottlenecks and ensuring data integrity. How does it handle, say, flow control if the receiver gets overwhelmed?
It provides inherent flow control built right in. Think
Okay.
of filling a bucket with a hose. If the bucket gets full, you want the water to stop, not overflow. In AXI, if the receiving component isn't ready, maybe its internal buffers are full, it simply holds its ready signal low. It deasserts ready.
Okay, so it pulls back its hand.
Exactly. And that action pauses the sending component. The sender sees ready is low and just waits, holding its valid data without any loss. It prevents buffer overflows. It's built-in back pressure.
That makes sense. But what about deadlocks? Is there a risk that both the sender and receiver end up waiting for each other forever, like a standoff?
Ah, good question. There's a crucial design rule to prevent that. The source the sender must not wait for ready to go high before it asserts its valid signal.
Oh, interesting. So the sender says, I have data, regardless of whether the receiver is ready yet.
Correct. Once valid is asserted, it has to stay asserted until that handshake eventually happens. This rule breaks that potential deadlock cycle where both might be waiting. It ensures things keep moving forward.
And because each AXI channel address data response has its own independent valid ready pair.
Exactly. They can all operate at their own optimal speeds. The address channel might be faster than the data channel sometimes, or vice versa. They don't hold each other back unnecessarily. Maximum throughput, maximum flexibility.
Okay, so let's quickly recap the states of this handshake.
Sure, if both valid and ready are low, 0, nothing's happening, no data. Destination isn't ready.
Okay.
If valid is high, 1, but ready is low, 0, the source has data, but the destination isn't ready. That's your back pressure, the sender is waiting.
Right, the pause button.
If valid is low, 0, and ready is high, 1, the source has nothing to send right now, but the destination is ready and waiting.
Eager receiver.
And the magic moment. Valid is high 1, and ready is high 1. That's when the transfer happens. Data moves on that clock edge. The handshake is complete for that beat. It's this continuous dance on every channel.
Okay, fantastic. Let's dive deeper then and break down the 5 distinct AXI channels. This is where we see those lanes of our superhighway really in action for both writing data to somewhere and reading data from somewhere.
All right, there are 5 channels in total. 2 for writing, 1 for write response, and then 2 for reading. Let's start with the writes. First up is the write address channel, usually called AEW.
AEW for address write.
Okay, this is where the master tells the slave where it intends to write data. Think of it like addressing an envelope before you put the letter inside and send it.
Setting the destination. So what key information goes on this AEW channel?
Several important things. First, a Wadagar, which is simply the starting memory address for the write burst.
The where.
Then Olin, the length. This specifies how many data transfers or beats are in this burst. Remember, one address can trigger multiple data transfers. This is crucial for efficiency.
Right, the burst length.
A size defines the width of each data transfer. Is it 8 bits, 16, 32, 64 bits wide? The size of each chunk.
How wide the data bus is, essentially.
Pretty much. And obers tells the slave how the address should change for each beat in the burst. Fixed means the address stays the same, maybe for accessing a control register repeatedly. INCR means increment the address for each beat, like writing to sequential memory locations. And wrap is for things like caches or circular buffers, where the address wraps around within a certain boundary.
Okay, that's quite a bit of control just with the address. Now, you mentioned something really clever earlier, AWID, the write address ID. Tell me more about that.
Yes, AWID. This is an identification tag. It's what allows a master to issue multiple write transactions before the earlier ones have even finished. They can be outstanding or in flight at the same time.
So the master doesn't have to wait for the first write to be fully acknowledged before starting the next one.
Exactly. This is a huge performance booster, especially when talking to slower slaves or going through complex interconnects. The interconnect, or the slave, can use these IDs to potentially process transactions out of order if they have different IDs.
Out of order. How does that work safely?
Well, the rule is transactions with the same ID must be completed in the order they were issued. But transactions with different IDs can be reordered by the interconnect or slave for maximum efficiency.
Got it. So it's like different lanes on the highway. Again, cars in the same lane stay in order, but cars in different lanes can overtake.
Precisely. It dramatically improves bus utilization and concurrency, and the handshake here is naturally all valid from the master saying, I have an address ready, and already from the slave saying, I'm ready to take it.
Okay, address sent. Next channel must be the data itself.
Correct. Next is the write data channel, or W. This is simply, here's the data. This channel carries the actual payload, the package itself, from the master to the slave.
And what are the key signals here?
The main one is W data, the actual data bits. Common widths are 32, 64, 128 bits, sometimes even larger, like 512 bits in high-performance systems.
That's a lot of data per beat.
It can be. Then there's WSTRB, the write strobes. These are really useful. They indicate which specific bytes within the wider WDT bus are actually valid for this particular beat.
Oh, so you can do partial writes, like writing just one byte on a 32-bit 4-byte bus.
Exactly. You don't have to write all 4 bytes if you only need to change one. WSTRB lets you specify which ones count. And finally, there's WLS. The masker asserts this signal during the last data transfer of the burst.
Ah, so the slave knows, okay, this is the final piece of data for this particular address request.
Precisely. The handshake signals are WVL'd from the master, here's data, and ready from the slave. I can take data now.
Now, you mentioned earlier that the write address AW and write data W channels are decoupled. How does that play out and why is it important?
Yeah, this decoupling is crucial for performance. It allows for really sophisticated pipelining. The write data on the W channel can actually show up at the slave interface before the corresponding write address on the ADW channel has been accepted or processed, or they could arrive simultaneously.
So the master doesn't have to wait for the address handshake before putting data out there.
Correct. This flexibility means the master can keep the data channel almost continuously busy if it has a lot of data to send, effectively overlapping the address and data phases of different transactions. It dramatically speeds up write throughput. Think of it like starting to load packages onto a truck even before you've finalized the exact delivery route details.
Very efficient. Okay, address sent, data sent. What's next? The confirmation.
Exactly. Channel number 3 is the write response channel. Or B, this is basically the slave saying, got it, or maybe not. It's the confirmation back to the master.
The delivery receipt.
Pretty much.
Yeah.
The key signal here is BRSP. This carries the status code for the entire write transaction. Did it work?
What kind of responses can you get?
The main ones are BR, meaning success. XOK is also success, used in specific coherent scenarios. Then you have errors. SLVR means slave error. The transaction reached the intended slave, but the slave had a problem, like trying to write to a read-only register.
Okay.
And deser means decode error. The interconnect couldn't even find a slave the address the master provided. The address was invalid.
Uh-oh. Wrong address.
Right. There's also beat on this channel. This is the ID tag that matches the AWID of the original write request.
So the master knows which outstanding write this response belongs to.
Correct. Vital when you have multiple writes in flight. The handshake is be valid from the slave. I have a response for you. And ready from the master. I'm ready to receive the response.
Now, here's a crucial detail you mentioned. A single response is sent for the entire burst, right? Not for each data beat.
Yes, that's very important. Even if you write, say, 16 beats of data in a burst, you only get one breast confirmation at the very end.
And what if an error happens mid-burst? Like the third beat causes an error.
Good point. Even if an error silver or deser is reported, the protocol dictates that the transaction must still run to its full programmed length. All the remaining data beats must still be transferred, though the slave can just ignore them after detecting the error.
Why do that? Why not just stop?
It dramatically simplifies the design of both masters and slaves, and especially the interconnect. Everyone knows a transaction of a certain length will always involve that exact number of transfers on the data channel. It prevents tricky situations with partial incomplete transactions that could mess up the system's state. It ensures protocol consistency, robustness over cutting it short.
Okay, that makes sense from a system design perspective. Robustness is key. So that covers writes, address, AW, data, W, response, B. Now for reads.
Moving on to reads. We start with the read address channel, AR, similar to ADW, but for reading. This is the master saying, I need data from this location.
Like submitting that request slip at the library.
Exactly. I'd like to borrow this book, please. The signals mirror the right side quite closely. You have ARADR for the starting memory address.
The where to read from.
ARLIN, RSize, and RBurst function identically to their right counterparts.
Mhm.
ALLIN, RSize, ABurst, defining the length, size, and addressing mode for the read burst. Again, enabling efficient block reads.
And crucially, I assume there's an ID.
Yes, ARID, the read address ID. Just like ARID, this allows multiple read transactions to be outstanding concurrently. A master can ask for data from several different places before the first piece of data even comes back.
And again, reads with different ARIDs can complete out of order, but reads with the same ARID must return data in the order requested.
Absolutely. That ordering guarantee for the same ID is critical for program correctness. But allowing different IDs to complete out of order maximizes bus utilization, especially if one read is fast and another is slow.
So seeing this mirroring of burst signals and IDs between AW and AR, it really highlights how AXI tries to be consistent, doesn't it? Makes designing logic easier.
It does. A lot of the control logic can be reused or adapted between the read and write paths. This consistency is part of what makes AXI powerful and relatively straightforward to implement despite its capabilities. The handshake, of course, is arvalid from the master and ready from the slave.
Okay, master has requested the read. Now the slave needs to provide the data. Channel 5.
Channel 5, the final one, the read data channel, or R. This is the slave responding, here's what you asked for. This channel carries the actual data from the slave back to the master.
The library returning the book.
Exactly. Key signals here are R data, the actual data bits being read. RIDE, which is the ID tag matching the original ARID so the master knows which request this data fulfills.
Makes sense. What about status? Is there an error signal?
Yes. RESP. Similar to BREST for writes, this signal indicates the status of the retransfer. You get OK, extos, case, selver, or disser, telling the master if the read was successful or if there's an issue.
And RLast.
RLast is asserted by the slave during the final data transfer of the read burst. Tells the master, this is the last piece of data for this request.
Okay. The handshake is arvalid from the slave. I have data response, and already from the master. I'm ready for data. Now, what's the key difference here compared to writes in terms of how the response is handled?
Ah, yes, a critical difference. Unlike writes, where the response, BRESSP, comes on a separate B channel, for reads, the response, RESP, is delivered on the same channel as the data, R data.
Oh, interesting. So R data and RESP travel together on the R channel for each beat of the read.
Exactly. Every beat on the R channel carries both the read data and the status for that specific transfer. This streamlines read operations. You don't need a separate handshake for a response channel. It reduces channel count and simplifies the flow a bit for reads.
But you still have that ordering rule, right? Even if different ARID transactions can complete out of order, the data beats within a single ARID transaction must arrive in the requested order.
Absolutely crucial. If a master asks for bytes 0, 1, 2, 3 with a single ARID, the slave must return the data for byte 0 first, then byte 1, then 2, then 3 on the R channel, each with its RESP. No shuffling allowed within a single transaction ID. Data coherency depends on it.
Okay, that clarifies the 5 channels and their roles. Let's quickly walk through how a full transaction unfolds. How does a typical write sequence play out using A, W, W, and B?
Sure. A write transaction starts with the master potentially asserting OVALID with address info, and WVALID with the first data beat simultaneously or close together. The master also needs to be ready for the eventual response, so it usually asserts ready early on.
Okay, master puts address and maybe first data out and says, I'm ready for the confirmation later.
Right. The slave, when it's ready, will assert all ready to accept the address and ready to accept the data. These handshakes might happen in the same cycle or different cycles. They're independent.
Got it. Independent handshakes.
Once the address handshake is done, the master continues sending the rest of the data beats on the W channel, asserting WVALID for each until it sends the last beat along with asserting WLast. The slave accepts each beat by asserting ready.
So data flows until WLast is seen and accepted.
Correct. After the slave has received that final data beat, the W channel handshake with WLast completes, it processes the entire write burst and then sends the overall status back on the B channel. It drives BRESP, with the status,
Okay.
okay, of error, etc., and asserts be valid.
And the master, which hopefully kept Brady high, accepts the response.
Exactly. When that B channel handshake, be valid and Brady both high, occurs, the entire write transaction is officially complete.
Okay, clear. Now, how about a read transaction using AR and R?
A read transaction is a bit simpler, channel-wise. The master starts by placing the read address and burst details on the AR channel and asserting are valid.
I want this data.
The slave asserts a ready when it can take the request. The AR handshake completes. The slave then goes off and fetches the requested data. This might take some time.
Okay, slave is working on it.
Once the slave has the first piece of data, it drives R data and the corresponding RESP status onto the R channel and asserts R valid.
Here's the first piece.
The master, which needs to be ready to accept data, asserts R again. The first R channel handshake happens, transferring the first beat. The slave continues this process driving R data and RESP, asserting R valid for each beat of the burst. For the very last beat, it also asserts RLS.
Master keeps asserting R ready to accept each beat.
Right. The entire read transaction is complete once the R channel handshake for that final beat, the one with RLSD asserted, occurs.
Got it. That sequence seems pretty logical. Now, we've used a few terms: transfer, beat, burst, transaction. Can we quickly clarify the difference? They sound similar.
Good idea. They can be confusing. Let's break it down. A transfer, or a beat, is the most basic unit. It refers to a single exchange of information on one specific AXI channel. It's defined by one successful valid-ready handshake, just one pulse of info passing hands.
Okay, one handshake, one beat.
Then there's a burst. A burst is a sequence of multiple data transfers or beats on the W or R channel that are all associated with a single address request on the AW or AR channel.
So one address request triggers potentially many data beats.
Exactly. Could be one beat for a non-bursting transaction, or 4, 8, 16, up to 256 beats in AXI4. This is where the efficiency comes from for moving blocks of data. You only pay the overhead of sending the address once for potentially many data transfers.
Makes sense. And a transaction.
A transaction is the whole enchilada. It's the entire sequence of operations across all the relevant channels needed to complete one full read or write request.
So for a write, that's the AW handshake, all the W handshakes for the burst, and the final B handshake.
Correct. And for a read, it's the AR handshake and all the R handshakes for the burst. It encompasses the entire process from the initial request to the final completion.
Okay, that's much clearer. Transfer beat is one handshake. Burst is multiple data beats from one address. Transaction is the full end-to-end operation.
You got it. And it's worth reiterating that key AXI concept. While the phases of a transaction, address, data, response, can be pipelined and happen somewhat independently across the channels.
For performance.
Right. But the actual transfer of information within each channel, each beat, is strictly synchronized by that valid-ready handshake occurring on a specific clock edge. It maintains data integrity at the fundamental level. It's cleverly asynchronous between phases, but synchronous within each transfer.
Efficient, yet precise. Okay, so we've covered the core AXI protocol, the channels, the handshake, but AXI isn't just one single thing, right? There are variations.
Exactly. Beyond this core protocol, which is often called AXI4 these days, AXI's true power also lies in its versatility. There are specialized variants tailored for different needs.
Like what?
Well, there's AXI4 Lite. Think of it as AXI on a diet. It's a much simpler, stripped-down version designed specifically for low-bandwidth communication, typically used for accessing simple control and status registers in peripherals.
So like turning an LED on or off, or
Yeah.
reading a sensor value, simple stuff.
Precisely. AXI4 Lite has some key simplifications. It only supports single-beat transactions, no bursts allowed. And the data width is typically fixed at 32 or 64 bits, much easier to implement if you don't need high throughput.
Okay, light for simple things. What else?
Then there's AXI4 Stream. This one is quite different. It's optimized for continuous high-speed, unidirectional data flow without any addresses.
No addresses. How does that work?
Think of it like a pipeline or a hose carrying a continuous stream of data. It essentially uses just the data channel concepts, like WData, WValid, Ready, LAMS, but without any associated address phase. It's perfect for applications like digital signal processing, DSP, networking packets, or video processing, where you have data flowing from one processing block to the next in a stream.
So point-to-point data fire hose, basically.
That's a good way to put it.
And you mentioned multi-core systems earlier. Are there special AXI versions for handling caches and keeping data consistent between processors?
Yes, absolutely crucial. Those are the AXI coherency extensions known as ACE and AC Lite.
What problem do they solve exactly?
Imagine you have multiple CPU cores, each with its own local cache memory, but they all share access to the main system memory. If one core modifies data in its cache, how do other cores know that their cached copies of that same data are now stale?
Right, that could lead to chaos if they use old data.
Exactly. ACE and ACE Lite add extra signals and protocols on top of AXI that allow caches to snoop on each other's transactions and maintain coherency. They ensure that all cores see a consistent view of memory, even with caching involved. ACE provides full coherency, often between CPUs, while AC8 provides I/O coherency, typically for peripherals that need to interact with the cache coherent system.
So, essential for making modern multi-core processors work correctly.
Absolutely fundamental.
AXI also seems to have some neat built-in features for squeezing out more performance. We touched on out-of-order transactions using the IDs. What's the real-world benefit there?
The big payoff is better bus utilization and lower average latency. By allowing the interconnect or slaves to reorder transactions with different IDs, AXI prevents a single slow transaction from blocking other, potentially faster transactions that are ready to complete. It keeps the data flowing more smoothly, making your system feel snappier.
And multiple outstanding transactions, being able to issue requests before the previous ones finish.
That directly enables concurrency. The master can overlap the latency of accessing one slave with the processing of data from another, or pipeline requests to the same slave. It's like a good project manager assigning multiple tasks without waiting for the first one to be 100% done before starting the next. Keeps resources busy.
And quality of service, QoS, that sounds important for real-time stuff.
It is. QoS signals, optional in AXI, allow a master to indicate the priority of its transaction. The interconnect can then use this information to prioritize access to shared resources, like memory. This helps ensure that critical, time-sensitive data like audio or video gets through with low latency, even if there's other, less critical traffic competing for the bus.
Guaranteeing performance for the important things.
Essentially, yes. It provides hints for arbitration.
And we mentioned configurable data widths earlier, 32, 64, 128 bits, etc. That flexibility must be really valuable for designers balancing cost and performance.
Hugely valuable. You can use a wide 128-bit or 256-bit AXI path for your main memory access, where you need maximum bandwidth, but maybe just a 32-bit AXI Lite interface for a simple configuration peripheral. It lets designers tailor the interconnect fabric precisely to the needs of each component, optimizing for performance where needed and saving area and power where high bandwidth isn't critical.
Now, in a complex chip with many masters and many slaves all trying to talk, how is all this traffic managed? You mentioned an AXI interconnect.
Right. You almost never connect a master directly to a slave in a real SOSN unless it's very simple. Instead, you have this crucial component called the AXI interconnect. Think of it as the sophisticated traffic management system for our AXI superhighway.
The central control tower and junction manager.
Exactly. The interconnect sits between multiple masters and multiple slaves. It contains things like arbiters to decide which master gets access to a slave when multiple masters want it at the same time, decoders to look at the address from a master and route the transaction to the correct slave, and multiplexers and demultiplexers to steer the data paths correctly.
So it handles all the routing, priority, potential conflicts.
Yes, it manages concurrent access, helps optimize overall bandwidth usage across the chip, manages different clock domains sometimes, handles data with conversions if needed, ensures QoS policies are applied. It's a really complex but essential piece of IP.
So AXI isn't just the road specification, it's the whole framework, including the traffic control system needed to build these complex SOCs.
That's a perfect way to summarize it. It's a comprehensive framework that enables high-performance, scalable, and reliable system-on-chip designs. It really did help democratize the process of building these incredibly complex integrated circuits.
Okay, let's try and bring this all together then.
Sure. At its heart, AXI offers this elegant channel-based architecture. Those 5 independent channels, combined with that simple but robust validator handshake. It provides a really clear, organized, and highly efficient way for all the different parts of a chip to talk.
And the way it decouples address, data, and response, plus features like bursts and those transaction IDs, that's where the real performance boost comes from, right? Through that parallelism and pipelining.
Absolutely. It allows different phases of communication to overlap, keeping the silicon busy and data moving quickly, which is what makes our modern electronics feel so seamless and fast.
And its impact goes beyond just speed. Its flexibility, scalability, and especially its standardization. That's simplified chip design massively.
Dramatically.
Yeah.
It fostered that whole ecosystem of reusable IP, shortened design cycles, lowered integration effort.
Mm.
It's been a huge enabler for innovation across the entire semiconductor industry. More new devices hitting the market faster because designers aren't constantly reinventing basic communication protocols.
And it's not standing still. You mentioned AXI 5 is now the successor, so it's evolving.
Right. AXI continues to evolve to meet new challenges. AXI 5 adds features for even higher performance, enhanced support for coherency, security features, and things relevant to atomic operations and reliability. It shows it's a living standard, aiming to be future-proof for the demands of next-generation computing, AI, and whatever comes next.
So really, AXI is one of those foundational technologies that most people never hear about, but that makes so much of modern life possible.
Pretty much. So the next time you seamlessly stream a 4K video on your phone, or open a complex app instantly, or just see some amazing new gadget hit the market,
Uh,
take a second to consider the silent, incredibly intricate dance happening inside that chip.
a symphony conducted by protocols like AXI?
Exactly. Which leads to maybe a final thought for you to ponder.
Okay.
How many other hidden superhighways of information, these invisible architectures and protocols, do you think exist just beneath the surface, quietly making our modern world possible?